Dear students, welcome back to the e-learning core 3, Fixed Income Analysis. In session 3, you will get an introduction to managing bond portfolios. In this context, we discuss the sensitivity of bond prices to interest rate fluctuations and introduce the concept of duration to measure the risk. Moreover, we consider refinements in the way that interest rate sensitivity is measured, focusing on the concept of bond convexity. Finally, we have a look at some passive investment strategies for managing bond portfolios. Now, let's start with session 3.1 and let's talk about interest rate risk and how it can be measured. The learning goal of this session is to introduce you to the concept of duration, which is used to measure interest rate sensitivity, meaning how sensitive do bond prices react to changes in market interest rates. The first question to ask is what the characteristics of interest rate sensitivity are. One fact we already discussed is the negative relation between bond prices and yield to maturity, meaning as yields increase, bond prices fall and vice versa. Moreover, another fact is that an increase in a bond's yield to maturity results in a smaller change than a decrease in yield of equal magnitude. This is because the functional relationship between the bond price and the yield to maturity is not linear, but shows some degree of convexity. Looking at the graph on the left-hand side, one recognizes the prices of long-term bonds tend to be more sensitive to interest rate changes than prices of short-term bonds. In particular, bond B, which has a longer maturity than bond A, exhibits greater sensitivity to interest rate changes. This is not surprising. If rates increase, for example, the bond is less valuable as its cash flows are discounted at a now higher rate. The impact of the higher discount rate will be greater as that rate is applied to more distant cash flows. Another characteristic is the sensitivity of bond prices to changes in yields increases at a decreasing rate as maturity increases. In other words, interest rate risk is less than proportional to bond maturity. In this context, note that bond B has 6 times the maturity of bond A, but it has less than 6 times the interest rate sensitivity. A further characteristic is that interest rate risk is inversely related to the bond's coupon rate. Prices of low coupon bonds are more sensitive to changes in interest rates than prices of high coupon bonds. For instance, bond B and C are alike in all respects except for the coupon rate. But bond B, the lower coupon bond, exhibits greater sensitivity to changes in interest rates. A final observation to make is that the sensitivity of a bond's price to a change in its yield is inversely related to the yield to maturity at which the bond is currently selling. To understand this, bonds C and D are identical except for the yield to maturity at which the bonds currently sell. However, bond C with a higher yield to maturity is less sensitive to changes in yields. On the previous slide, we have seen that the price sensitivity of bonds to changes in the interest rate is affected by many factors, which are all related to the effective time in which the cash flows are received. A measure that summarizes the sensitivity of bond prices to changes in the yield to maturity is duration. The concept of duration is so important to analyze interest rate sensitivity so that we give a proper definition. A bond's duration is the weighted average of the maturity of individual cash flows, with the weights being proportional to their present values. We define the weight Wt associated with the cash flow made at time t, denoted as CFT, as follows. The numerator on the right-hand side of this equation is the present value of the cash flows occurring in time t, where y is the bond yield to maturity. The denominator is the value of all the bond's payments or simply the bond's price. These weights sum to 1 because the sum of the cash flows discounted at the yield to maturity equals the bond price. Using these values to calculate the weighted average of the times until the receipt of each of the bond's payments, we obtain Macaulay's duration formula. To illustrate the concept of duration, have a look at the following example. Assume two bonds, an 8% coupon bond making semi-annual coupon payments and a 0 coupon bond, each with a maturity of 2 years, a yield to maturity of 5% and a face value of 1,000. Applying our duration formula introduced before to the 8% coupon bond, it follows that the bond has a duration of 1.8852. Note that the coupon rate is given on an annual basis, but coupon payments occur semi-annually. In order to consider this fact, we have to divide the coupon rate by 2 and obtain a coupon payment of $40 every 6 months. The duration of a 0 coupon bond is very simple to compute, since it corresponds to the bond's maturity. This result can also be derived by applying the duration formula. Since the 0 coupon bond pays only one cash flow at maturity, the numerator equals time to maturity times the bond price, while the denominator is equal to the bond price. It follows that for a 0 coupon bond, the duration equals time to maturity. The duration of the bonds used in the previous example can easily be computed by using a spreadsheet program like Excel, as depicted below. For example, for a 0 coupon bond, the weight in column F is equal to the present value of each payment in column E divided by the bond price in cell E8. The duration is obtained by multiplying column C times column F and summing up. Another way to think about duration is in terms of elasticities. Duration is the elasticity of the bond's price to changes in the average interest rate. More specifically, by how much will the bond price approximately change when the yield to maturity will change by 1%, say from 10% to 10.1%. Define capital Y as 1 plus lowercase y, where lowercase y is the yield to maturity and let P denote the price of the bond. The elasticity is then simply the negative of the percentage change in the bond price dP over P, divided by the percentage change in the yield to maturity dy over y. For a coupon bond, the price is obtained by the by now well-known present value formula. In order to compute the elasticity, the bond price is substituted into the elasticity formula above. Taking the derivative of P with respect to Y and some rewriting implies the duration formula we are already familiar with. Since we have now a firm understanding of the concept of duration as a measure of interest rate sensitivity, it is time to summarize the most important duration rules that should be remembered. Rule number 1. The duration of a 0 coupon bond is equal to its time to maturity. This corresponds to a 45-degree line when maturity is depicted on the x-axis and duration on the y-axis. The second rule tells us that holding maturity constant, a bond's duration is lower when the coupon rate is higher. Rule number 3 tells us that when holding the coupon rate constant, a bond's duration generally increases with its time to maturity. It follows that duration always increases with maturity for bonds selling at par or at a premium. Rule number 4 says when holding other factors constant, the duration of a coupon bond is higher when the bond's yield to maturity is lower. The intuition for this property is that while a higher yield reduces the present value of all of the bond's payments, it reduces the value of more distant payments by a greater proportional amount. This further implies that at higher yields, a higher fraction of the total value of the bond lies in its earlier payments. The final rule, number 5, tells us that the duration of a perpetual bond equals the ratio of 1 plus the yield to maturity divided by the yield to maturity. Note that this rule is derived and consistent with the formula for duration used before. The proof is straightforward. By substituting the price of a perpetual bond in the elasticity formula used before and taking the derivative of that price with respect to the yield to maturity denoted by lowercase y, the corresponding duration measure is obtained. So far, we had a thorough look at the concept of duration. We know that the duration is the elasticity of the bond price with respect to its yield to maturity. So, for example, the yield to maturity increases by 1%, say from 10% to 10.1%, then duration tells us by what rate the bond price is supposed to change. However, it seems to be more natural to talk about changes in yield to maturity or changes in interest rates rather than about a percentage change in these variables. We would rather like to know what the price impact is if the yield to maturity increases by 10 basis points. However, such an interpretation can quite easily be achieved by modifying the duration formula. This new duration measure is called modified duration, since we only have to divide regular duration by 1 plus y, where y denotes again the yield to maturity. To illustrate modified duration by an example, consider a 4-year bond with a face value of $1,000 and a coupon rate of 4%. The yield to maturity is 5% and the current bond price is $964.54. The duration of the bond is computed by using the corresponding formula and is 3.7704 years. Modified duration is duration divided by the yield to maturity, which is 3.591 years. Suppose now that the interest rate increases by 25 basis points or 0.25%. The modified duration formula then implies a decrease of 0.898% in the bond price. A direct calculation of the bond price using the higher yield to maturity of 5.25% implies a bond valuation of $955.93 and a 0.892% decrease compared to the former market price of $964.54. After having carefully studied session 3.1, please start with the review questions.